Hey, how are you?
Doing well, dude.
How was your weekend?
Pretty good.
Good. How did you find the midterm?
Fine.
Okay.
So definitely different from any of the other midterms I've taken,
Okay.
with it being online.
You mean it's easier in terms of like the questions or like flexibility?
It's easier.
Oh, you said
It's different.
oh I thought you said easy. Okay, okay. It's because like you mean it's different meaning like you have a whole day?
Well, yeah, you have a full day and it's like through web courses. That's just like a solution to check out. And it's
Oh,
like interesting. Like I've just never taken an exam like that. So
okay, okay.
yeah, it was definitely a good experience.
Okay. Yeah, I think all the other midterms are like either in person and then you have like some, have to do a little bit of hands-on, like pen and pencil,
Mhm.
or it's like online but multiple choice, like a quiz form. So that was kind of a little bit different.
Mhm.
But hopefully it wasn't like anything too like irregular because like it's similar to the homeworks in essence, so should be straightforward.
That is what I like to do. So
Mhm. How are you? How was everything?
Good. I was on campus pretty much
Okay.
all day.
Uh-huh.
So I'm like,
Stop by.
yeah, go in person.
Okay, nice.
Most of the time I've just been online for these classes just because it's my only class of the day.
Oh, okay, okay. And are you enrolled online or the in-person section? Like which section are you enrolled of the class? Because there we have two sections. Oh, you didn't know that.
I did not.
We had two Oh, you didn't know that either? No.
So
Yeah, I know that you're on campus for almost every day on the week, but this class we have two sections. So we have one section that has 150 students, and we have one that has 40. So but it's kind of the same for both. So the web course is combined into one. So
well,
yeah,
yes.
yeah,
So the thing is, you teach in person, but you also have the Zoom up.
yeah,
So like anyone can tune in.
yeah. Anyone can, yeah. So if you're signed up for in person, and then you don't feel like coming, or if you have something to do, you can just attend the Zoom.
Yeah, so I did sign up for in person.
Yeah, that's fine. That's fine. Cool, cool.
I had a really this year. Because I was able to get most of the midterm done,
Okay,
but I was like, okay. I just didn't have a lot of time to finish the rest of it because my courses was down. I'm like, well, I'm just gonna do the rest of it like sometime tomorrow on campus.
uh-huh,
But I didn't realize, like, I was busy the entire time on campus.
yeah, yeah.
So,
That was the thing because usually some students on Tuesday they are more busy than Monday. But for the students that got a head start a little bit on it, which you can't really get a head start because well, course was done around 3 a.m. and the midterm was released at 12 a.m. So unless like you accessed it at like that time, then you would have been able to see it. Otherwise,
obviously, it went down at 3 and then came back up at 7.
41. Yeah. Yeah. Yeah, 7:16 exactly. Okay, we can go ahead and begin. We're at the 4:30 mark. Just to get a thumbs up from everyone on Zoom, if you can hear me, that'd be appreciated. So let us go ahead, you know. Thank you, Aiden. Okay, so let's speak a little bit about course logistics, where we are in the class. So we're currently in week 10. Last week we wrapped up chapter 2, which is the transport layer as a whole. And the last part that we spoke about is a congestion control and how does TCP deal with congestion control and what are the several algorithms, whether it's end-to-end approach or the network assisted approach. And we spoke about different algorithms within these approaches. What we have today is, and then last Wednesday was a review kind of, so there was no class. And then we had our midterm on Monday. Hopefully it wasn't too difficult. It was something like similar to the homeworks and something that you have already seen or maybe that we discussed in class. So I hope that everyone did well and the grades will be due by sometime next week. So you should be able to see your grades for that. But yeah, that is it. That's all what we have for the course logistics. And today we're gonna start a new chapter, primarily chapter 4, which is about the network layer. So do we have any questions? You guys don't have any questions for me? Okay, good. Okay, so let's go ahead and begin. So as usual, the lecture is recorded and some of the slides are borrowed from the book, and you can access these over in that link. So before I want to speak or we dive into the network layer itself, I wanted to speak about where we are exactly. So we said that we wrapped up the transport layer last week, and I want to differentiate between the transport layer and the network layer. And I brought this analogy back up from the last lectures that we talked about to tell you that differentiation between them, between the network layer and the transport layer. You said when we speak about the network layer, it is logical communication between the hosts. So, and that is what we're going to be talking about in this chapter and the following lectures that we will speak about. Transport layer we talked about is communication between the processes or the sockets on the given application. So it relies on the net on the layer service, and they go hand to hand. And we said an analogy to give you that depicts the idea of the network layer and the transport layer is that we have a household analogy of 12 kids in an house that are sending letters to 12 kids in their house. The hosts are going to be the houses, so there is where the letter is getting sent from. The processes is the kits, and this is primarily the transport layer that we talked about. And the app messages are the letters in the envelope. These could be called processes. You can call them as the sockets that are connecting the interface of the application to the interface of the receiver. Okay, and the transport protocol is Ansible, which demultiplexing to the in-house siblings. And the network layer protocol is the kind of like the postal service here that we have. So these kind of go hand to hand. So when we deliver a message from one house to another, we are using the network layer. But when we want to send something to specifically inside the house, we use the transport layer that can deliver it to someone specific, like a kid, one of the 12 kids in the house. 12 kids in the house is, I think, quite a lot, but you get the idea. So here's usually our kind of like our figure that we have some demonstration with to show the idea what we have. So obviously we spoke about the application layer. We said we have a bunch of applications. These applications have different uses, and the applications are going to be different based on the developers. But we spoke about some protocols on the applications. Once we have a message that goes from the application down to the next layer, which is goes down to the transport layer, then the transport layer would add a segment to the message. It's going to add or determine the segment header values that we spoke about in chapter 2. It's also going to create that segment, whether it's TCP or UDP, and then it passes down to the IP. So here we are going to talk about the network layer and the characteristics of the network layer as we make our way down from a top-down approach. So obviously the network layer is responsible for delivering the message to the other host, or delivering it to another router, another hub. So you get the idea. And then from the receiver side, it will also go down to the transport that receives the segment from the IP. We want to make sure that the file or the data that is sent is exactly what is supposed to be received. After we verify that and we extract that information, we deliver it to the user, so the application. But when we talked about the transport layer, we spoke about various things. We spoke about ports, demultiplexing, multiplexing. We talked about reliable data control with RDT1, RDT 1.0, RDT 1.0, RDT 1.1, and 2 and 3. We also spoke about congestion control, flow control, finite state machines, so that you should already have a foundation or understanding fully of the transport layer, how it works. So now we're going to talk about the network layer. So this is the beginning slide of the network layer of the lecture. So we said the network layer is responsible for host-to-host delivery across different networks. And we want to understand the main principles behind the network layer, and we want to focus on what it does. So we'll focus on the data plane, and the data plane itself is where the actual packets forwarding happens. So give me 1 second. That is good. Give me one moment, guys. Give me 1 second. It wasn't shared for Zoom. Yes, so we'll focus on the data plane when it comes to the network layer. And this is where the actual forwarding happens. Under this specific network layer or this specific chapter, we'll also study the network layer service models. And we'll see what type of services the layer can provide. We'll talk about forwarding versus routing. Forwarding is just basically we are forwarding data, but routing is basically a path selection. So we have to have a specific algorithm that routes based on time, that routes based on congestion, that routes based on a couple of features. We'll talk about how a router works, so how packets are processed and forwarded. We'll talk about addressing, and that is kind of related to subnetting, how devices are uniquely identified on the network. We'll talk about generalized forwarding, which is a modern, flexible forwarding rules used in software-defined networking. We'll talk about internet and architecture and see how all these components come to form the internet. We'll also talk about we'll talk about we'll look at how these specific principles are going to be implemented in real network. So we look at the IP protocol itself, which is a layer 3 protocol related to the network layer. And we want to address how the packets are delivered and addressed. We'll talk about NAT address translation and middle boxes, where we modify or manage traffic as it moves through networks. So together, these topic links or these header links are what we're going to study in this layer and in this network layer or this chapter. And we want to see how the network layer operates. So this is going to be our usual roadmap that we have for every chapter. And today we will cover the first part of it. So, so this slide gives us what we're going to study as a whole for this chapter as overall. So we're going to study the network layer as an overview, which has two main components. We have the data plane and we have the control plane. And we said the data plane is responsible for forwarding packets. The control plane is responsible for routing decisions, and that is essentially the brain. We'll also look on what's inside a router. So we'll discuss input ports, switching, and output ports, which are the key blocks in a router that would move packets through the router. We'll talk about buffer management and scheduling. And we know that the router has a buffer. We decide how packets are stored and transmitted during congestion. Then we'll talk about the IP protocol itself. So we'll learn the datagram format, the structure that defines how the information travels. We'll study addressing. That's the system that identifies the device on the network. We'll also study addressing. So network address translation, NAT, where we have multiple IPs or multiple devices that share one single IP. So we can have an organization that has one specific organization of a network infrastructure that are private, so they are using private IPs. But once they reach out to the external network or the default gateway, they would have one public IP, which is done by using NAT. And then we'll touch on IP version 6, which is the newer version of IP version 4. And we know that it has been designed and designated to expand address capacity. Then we'll talk about something modern more and now generalized. So we'll talk about generalized forwarding and software defined. So the idea here is going to be a match in action where routers or switches decide what to do with the packets based on rules, on given rules that we set as developers or admins. We'll look at OpenFlow, which is a real-world implementation of this match plus concept. And then finally, we said we'll study middle boxes, and these are devices like NATs, firewalls, load balancers that would sit between the routers and influence traffic behavior. So by the end of this roadmap, you should understand the network layer as a layer, as it's in a big idea, but obviously every point on this roadmap is going to be we're going to study in detail. So we're going to introduce the network layer and services protocols. So this usual figure that we have, and we have overseen this figure in multiple chapters, is obviously we have different things that are going on, different enterprises, different infrastructure of networks. We have a lot of routers. We have a lot of paths between these devices, between these hosts. We have a mobile network. We have a data center. We have national or global ISPs. But now we are studying the network aspect of this given figure. So we usually have this on the sender side, when we have a receiver side. On the sender side, the network layer would encapsulate. This is giving you a high-level idea. So the network layer would encapsulate the transport layer segments into a datagram. Then it would pass them down, obviously, to the second layer, the link layer, because now we moved from the application and transport layer, we're now at the network layer. On the receiver side, the network layer would receive the datagrams from the link layer and delivers the segment to the transport layer. And then that goes back and forth between the sender and communication across different networks. We have that the network layer exists in almost every device. So you can see in almost every router, there is the internet or the network protocol that includes the host and routers. So each device runs the network layer to process and forward packets. So if we want to send packets, every path or every stop or every hop needs to have the network layer that can either forward the packets or move them somewhere else to our destination or where we want them to be. And then we'll look specifically at routers and see how they work as well. So we want to study routers themselves and how they move data across the internet. So we'll examine header fields, we'll examine the datagrams, we'll talk about the inputs and output ports. So this should give you the general idea or the process of what makes global data transfer is possible. And this is what users, or this is the back end of what's going on when users are using various applications on a day-to-day basis, where we're studying them and understanding these specific techniques or these protocols. So we said the network layer has two responsibilities. The responsibilities are routing and forwarding. Okay, so we'll start with forwarding. This is the process of just moving packets. So forwarding is basically, I give you a piece of paper in this given room, and you are forwarding the paper to other students in the given room. So that is the idea of forwarding. So that is one responsibility of a network layer. You can think of it as a local operation that happens inside the router. So every time a packet arrives, the router would look at the destination and forward it to the next hop. Now, routing is a little bit not local, so we are thinking external. So maybe I give you something, a paper, and you have to move it to another department or another building. So, and with the path that you take, there's obviously various paths that you can take, and you have to study which path is the smartest and most efficient. So, and we talk about algorithms when it comes to routing. To give an analogy outside of the network layer functions, which are forwarding and routing. So to make it more intuitive, let's take an analogy of taking a trip. Forwarding would be just like getting through a single interchange or intersection. So it's one small local movement. And routing is like planning the entire trip from your start to your final destination. So these two functions are the main two functions when we speak about the network layer, basically forwarding and routing. So the two main functions are routing and forwarding, and the network layer is divided in two main components into two. So the first one that we have is the data plane, and we have the control plane. So each of these play a different role on how the data moves to the network. So the data plane is local. It's per router function. So it determines how a datagram arrives at a router and how it's forwarded in an appropriate manner. So this is the actual movements of packets inside each router. And that is basically, we have obviously a packet of data that is arriving, and we have number of bits within the packet, and it's going to be forwarding that. And we have the control plane. This operates on a network-wide level. These are how the datagrams are routed among other routers, and think of end-to-end path. So from source to host, from your starting trip to your end trip. So this is where logic, coordination happen. The control plane will tell each router which path to follow. So we have two main approaches when it comes to that. We have traditional routing algorithms that are set in place, and we have software-defined networking. So when we say about traditional, this is basically already implemented inside each device, inside each router. Software-defined networking is where the routing decisions are made in a remote or centralized server. So they are getting a message or a decision or an input from a router, from a centralized server or somewhere remote to make these decisions. So together, these two, the data plane and the control plane, is is the complete view of how the network layer functions in practice. So to talk a little bit about software-defined networking, and what it does, it's basically where software decides. So as it states, software-defined networking, software is going to be deciding how the data flows. And we have a central, like we said, a remote or a central server that manages and configures these devices instead of each one being managed separately. So rather than having each device or each physical device manage itself, we have something that is a hub that controls all these devices. The controller would combine or unite, as you say, all the physical and virtual devices into a single programmable system. And we still have the control plane and the data plane. So we said the control plane is going to be software protocols that make traffic decisions, and data planes are going to be the physical devices like switches, routers that actually forward the data or forward the packets. Here's an idea to give you a little bit about traditional and the SDN architecture. So in the traditional networks that we had before software-defined networking, we had obviously the physical devices as we see now, but each of those devices has control over its own data plane and control plane. So that means every device would make its own decisions. And you can see how that could be complex over time, where we need manual configuration or manual management over each specific device. So that's where the control plane centralized in a single SDN controller comes in and makes all the traffic decisions and routing. And simply all the devices would follow these instructions. So they handle the data plane. So the benefit of SDN is going to be that it's easier to configure, automate, and network-wide policy control from one place. So you can see in traditional that each switch or virtual switch or a router would have a control plane and data plane. And SDN, we get rid of the control plane for every device, and it's linked to a hub that would control all the other devices and make the decisions or the routings for those. So the architecture of SDN is going to be divided into three main layers. We have the application layer, we have the control plane, and obviously the data plane. So when it comes to the application layer, this contains any network applications like web applications, any typical application that we would use. And we have APIs, application programming interface that links the layers. So allows the application to request network actions through the controller. The control plane is going to be making the decisions, makes the routing decisions, forwarding, blocking, forwarding, and the data plane is going to be the physical devices. So whether it's virtual switches that we have are virtual routers or physical routers. So does that make sense where software-defined networking comes in? So key advantages, we have one centralized management. So we don't have separate control and data plane. So it's unified. It's also cost efficient. So the SDN would allow advanced network functionality using simple, less expensive hardware. And it's also flexible and scalable. So networks can quickly adapt to new application users and policies through software updates instead of physical changes. Also for cloud integration, there's also one advantage of software-defined networking, how we can manage remote and cloud-hosted resources. That is extending on or beyond the physical devices or the on-site devices that we have on the network. So now that we have understand the difference between data plane or control plane and the traditional way in software-defined functions or mechanism, let's focus on the per router control plane that operates inside individually on each router. And we said that every router has its control plane components that interact with other routers. And the control plane is the brain you can think of that would handle the logic and coordination, while the data plane would forward the actual movements. So here we have data that is coming in, so values that are arriving in the packet header. And then we have various routers that we have to go through, obviously. So you can see that there's multiple routers in the networks. We each are represented as a cylinder to highlight that it contains its own control logic. So those are going to be existing in every router, not just one router, right? So inside each router, what we would have a local forwarding table. This local forwarding table will help us map header values to the correct output ports. So when a datagram arrives, the router would examine the header, saying, what does this header match to? And then we can see which link interface or which output we forward it to or route it to. So that is the idea. And this is going to be obviously these tables inside each router is going to be continuously updated and maintained by the router's control plane components. We have the routing algorithms. So that would, how each router communicates with the others or how they exchange information. And this is going to allow the routers to learn about the overall network structure and discover the most efficient paths for packet delivery. The red lines here, it's going to be a representation of communication links between the routing algorithms. And we see that here the routers are working together, each running its own algorithm while sharing data to stay synchronized. So even though that we have the routing logic is distributed across multiple routers and it can be different, they operate as one unified control system that ensures consistency and reliable data packet delivery. And then finally, we would have the control plane and data plane that we spoke about. The control plane itself is going to be computes and installs the forwarding rules, while the data plane uses these rules to forward the data. So that is the separation that makes our life way easier and more efficient for us to have the overall internet scalable, flexible, and resilient. Now that's kind of the traditional way where we have each router making its own decisions, and it has its own control plane and data plane. So we want to see how SDN works when it comes to control plane. So the control plane of each router that we've seen in the previous slide is going to be moved out the routers and placed in a centralized remote controller or a server. So this is going to be responsible for all the routers. So just like before, we would have different routers and they're represented as a cylinder. But these are no longer individual model routers that would make their own decisions. They're going to be relying on one unified controller. So the large component above these routers is going to be the remote controller. This controller has global view of the entire network. It's going to be basically the remote controller that can compute optimal paths for data flow. So by us making this centralized, it becomes very simple in terms of management and allows faster updates across the whole network. And then we have the forwarding tables as well. And these are going to be, that is going to be the distribution of how we can forward the data or the packets that arrive. So rather than having these local tables locally as well, we would have them with the controller. The controller can read those on its own, and then it can route. And then obviously we have the red lines here that shows CA. That stands for the communication channels between the controller and routers. So the controller would continuously monitor the network and update the routers wherever changes occur. And then each router has a CA, control agent, and that communicates directly with the controller or the remote table. So then finally, we want to see the highlight of the control plane and data plane. Usually the control plane just got changed by SDN or the remote controller, and the data plane performs the forwarding as usual. Nothing has changed in terms of the data plane. It's only receiving its decisions from the higher up or the remote controller. So that is the traditional or software-defined forwarding or software-defined networking when it comes to forwarding and routing data or packets. So we want to talk about the service models. And basically, we want to see how does data that is transported across the network from sender to receiver? So the question that we want to ask ourselves is we want to say, what kind of service does the network layer provide for this communication channel? Or like, is there any guarantees that can be made? Can the network layer offer any guarantees when sending datagrams or forwarding packets? So let's start with a example for individual datagrams. So we have one possible service is guaranteed delivery, meaning the network assures or confirms that the data is going to be received or sent over to the destination. We could have another possibility of or guarantee that the delivery is made within less than 40 milliseconds delay. So these services apply to single datagrams, so treating each packet individually of others. Another service that we could have as an example is the flow of datagram, meaning the sequence of packets that belong to the same session or connection. So we want to talk about per flow. So we want to see, does the network provide an order datagram delivery? Does it ensure that packets get delivered in the same sequence they were sent? Also, another example of a service could be like guaranteed minimum bandwidth. Can we reserve a specific data rate for the flow? So we want to see, can we guarantee, can the network layer guarantee these various services? Can it achieve these or not? So we will study the network layer more in terms of as a service model. So we talked about the different service models in theory. So let's look at the actual service, the model used by the internet today. So that is, the model is using, it's called the best effort service model, meaning that it does its best to deliver data, but it does not guarantee any specific level of performance. And then we have the right side of the table that shows quality of service guarantee. Can the current internet service model today assure that bandwidth, loss, order, and timing can be guaranteed? No. So it does not have any of these that will guarantee. So basically, the best effort model, there is no guarantees. So whether a datagram will be successfully reached by the destination, that cannot be guaranteed. The timing or order in which packets are delivered is not also guaranteed. And same as for the bandwidth that will be available for end-to-end flow. So in other words, we can say that packets could arrive late, they could arrive out of order or not at all. And that's completely acceptable under this model. So despite the limitations that we have, the best effort model has been proven to be simple, scalable, and efficient. So that's why it remains as the foundation of today's internet, because not only we rely on the network layer as itself, we rely on other layers that would help us and assist aside from the network layer. And this is going to basically compare other service models or network architectures that we have. We said that the best effort service model provides no guarantees. We have ATM, which is a synchronous transfer mode, where networks used these are used before modern IP networks, is designated for high speeds, connection-oriented communication with strict quality of service guarantees. We also have CBR and ABR, so the constant bit rate and the available bit rate. So the constant bit rate is a service in ATM that guarantees a fixed data rate and provides full control over delivery, order, and timing. So you could see yes and no's in comparison to the best effort model that we have up there. The ABR service offers a guaranteed minimum bandwidth that we have, and but it does not ensure timing or loss, suitable for non-real-time traffic. So it's kind of like UDP and TCP and what they offer, and how, if we were to compare them, what would they offer? And then the internet later introduced INTSERV, integrated services, using RFC 1633 that provides per flow resource reservation. And then we have different serve that uses RFC 2475, and these are coming exactly from the protocols themselves, or from the IEEE, that prioritizes network classes for better efficiency. So We have different service models that have different trade-offs between the guaranteed performance and scalable and to network design, but the internet today uses the best effort model. So now that we have discussed that the network today is using the best effort model, we want to see why it has been so successful despite its offering no formal or any type of guarantees. And it might sound, when we compare this to other models, it might sound unreliable, but it actually has several key advantages that made it practical and scalable for use. So the first reason it's simplicity of the mechanisms. And the internet does not need to reserve resources or guarantee any deliveries, so it's easy to deploy and manage. And the simplicity allowed the internet to scale quickly and adopted worldwide. The second advantage or the second reflection that we have is sufficient bandwidth, meaning that most of the time there is enough capacity for the data to flow smoothly. So even though the internet does not guarantee performance, the available bandwidth often makes experience good enough for real-time applications like voice and video. Third thing is that internet relies on replicated application layer distributed services such as data centers or CDNs, which is content distribution networks that are related to more like YouTube and Netflix. So these systems bring content closer to users, and we have these servers deployed everywhere, and that reduces delays, increases reliability, and can even offer a best effort network. Obviously, we have congestion control or elastic services like TCPs, and we said about TCPs in the last chapter with the transport layer, and we see how it provides these mechanisms for us. So these specific protocols automatically avoid congestion, making the network more efficient and without requiring to guarantee quality of service. And finally, it's hard to argue the overall success of the best effort service model, despite its lack of guarantees. It is mostly wide used today. It's proven to be flexible, scalable, and effective. And with the other protocols that we have and the other layers that we have in those protocols. So we discussed the network layer overview. This is our roadmap. So we talked about the data plane and control plane. We talked about traditional software-defined networking and SDNs. We talked about the best effort model. So now it's time to look at what is inside a router. And we said there's at least several characteristics. So let's go ahead and begin. So now that we controlled and now that we have covered the data plane and the control plane conceptually, we want to open the router and see on look at its internal structure. So this slide will show a high level view of a generic router architecture. So focusing on the major components to handle forwarding. So every router has two main sites. We have an input ports. This is where packets arrive or enter. And then we have output ports, as you see on the right hand or the right side of the slide. This shows where packet leaves. Between these ports, we have a high-speed switching fabric, and that acts as the internal or highway of the router. So the job of that is to transfer packets from the input to the output as quickly as possible. And the switching fabric is designated for extremely high throughput, since it handles all the internal traffic. And above, we have the routing processor. This component uses the router software that manages the routing protocols, updates, forwarding tables, and makes decisions. So the routing processor is going to be like the brain of the router. And it's responsible for all higher level control functions. And then together, these parts illustrate the separation of the control plane and the data plane. That are the two main functions of the network layer. So we said the control plane is going to be software, the SDN, and operates in milliseconds time frame. Forwarding is going to be hardware that operates in nanoseconds of a time frame. So this is the overall architecture that for a given router and what will be included in the given router. So again, we have router input ports and router output ports. We have high-speed switching fabric in between, and we have a routing processor, and we have our two functions for routing. And basically the brain or the routing processor. And the forwarding data plane is the way that data gets forward. So we want to zoom into one component. We have seen the higher level component or architecture of the router. We want to look at the input ports and just the input port. So we said the input port in the last slide is the left side. So we want to study that in detail. So we said that this input port is where incoming datagrams enter the router before forwarding to the switch fabric. So its main job is just to receive the bits from the physical media, process them, and prepare them for switching. So the first stage or that's inside the port is called line termination function, which operates as the physical layer. So this layer is responsible for bit level reception. So it converts the incoming electrical or optical signals into bits that the router can process. So this is where raw data comes through on the physical media that we have. Then we have the link layer protocol. And this is something that we're going to discuss more on chapter 6, but to give you an idea is that this component handles frame reception. So ensuring that frames are recognized, validated, and extracted properly. So for example, using Ethernet. So the link layer prepares the frame for the network layer so the packets can be processed and extracted and forwarded correctly. And then finally, we have the packet reaches the lookup, forwarding, and queuing selection. And this is where everything takes place. So here the router is going to perform decentralized switching. It's going to be basically meaning that each input port uses its own forwarding table to determine the correct output port. So this process uses a lookup. This process is going to use a match plus action approach. So it checks the packet header fields and applies the corresponding forwarding rule. So the goal of this is to complete all the forwarding at line speed fast enough to keep the incoming data coming in, because we obviously have a queue and we need to deliver everything in the queue in time such that new data can arrive and be forwarded more efficiently. So we said the plus and match action method is where the router checks the packet headers and finds the matching rules and applies the forwarding action. So we have in-destination based forwarding and generalized forwarding when it comes to the idea of forwarding. So for destination based, the router would look at the IP address to decide which port to use. This is the traditional and most common approach in IP networks. And then we have in-generalized forwarding, where the router can look at the segment of the frame and can match multiple header fields. So if this header field matches what we have, such as a source or a protocol type, maybe a port number, so that allows more flexibility where we can forward the data, not only based on the IP address, but we can also forward based on other features or characteristics that would come from the header of the packet. So here we see destination-based forwarding, and we have a forwarding table, obviously, that we said. And this table that we said we have in every router, that is the local table. This decides where we can forward stuff. So the router would examine the destination IP address in each incoming packets, and then matches it to a specific address range in the table. And then each address would correspond to a link service, a link interface that we see on the right-hand side, indicating which output port the packet should be sent to. So we have incoming packets, we have destination range. If the new destination falls between the specific range, then we use link interface 0 or 1 or 2 or 3, depending on what range falls under this exactly. So if the address that we have doesn't fit or it doesn't fall under a defined range, then the router would send it to the default interface that we have, and that is shown as 3. So we have various options or various table various forwarding addresses in the table. If they match any of these ranges, we use these specific interfaces. If not, we use the generalized set default interface. But sometimes addresses don't divide evenly, meaning that certain addresses patterns can overlap or fall between defined ranges. So in those specific cases, we need a more advanced technique. And this is where we're going to talk about longest prefix matching to find the most specific match for that address. So when destination addresses don't divide cleanly, we said we use the advanced technique, which is longest prefix matching, to make the forwarding decisions that we have. So the idea is going to be very simple. Among all the entries that match a packet destination, the router chooses the one with the longest matching prefix, meaning the most specific match that we have. So that ensures the packet follows the most precise route available. So here we have different patterns, prefix patterns, associated with specific output interfaces as usual. So for each incoming destination address, the router would check all the entries and selects the one with the longest prefix, but the longest prefix that still matches the address. So that prevents ambiguity when multiple entries overlap, because that could happen. So if we have multiple entries, we use longest matching prefix. So at the bottom, we see two examples of destination addresses that would come. And the question that we say here is which interface should the routers follow, or which link interface we should give them. Here we use the longest prefix as the matching for us and to see where they fall under. So we take the first longest prefix. So that is going to be the 1-0. That is a match that we would have, obviously. Obviously, we have 1-0 that would matches 1-1 at the bottom with link interface 2 does not match. So that is one match that we have. So we have one match so far, but that is not the longest prefix match. So let's look at the longest prefix match. And then we have another match here that we see. Since we don't have another match for this specific address, this is going to be the longest that we have. So that is a match, and then we can use link interface 2. But we're still stuck with the idea of the longest prefix match. So that is going to be the longest prefix match based on the incoming and based on the range that we have. So the idea is that we match the numbers or the incoming addresses to the best that we can, or based on the last matching, and then it would deliver to that link interface. Before we move on, we want to quickly discuss why we use prefix matching. And we want to study how the routers actually perform longest prefix matching in hardware. So we'll explain why this method is important in more detail when we study IP addressing. But for now, we want to know what's the key to most routers that use CAMS or itinerary content addressable memories to speed this process. So a content addressable memory works different from the normal memory. So instead of looking up a value by address, you present the value itself, and the memory tells you if it matches. So that means the router can retrieve a match in one clock cycle, regardless of how large the forwarding table is. So modern routers use this terminology, like Cisco Catalyst can store around 1 million routing tables or routing entries, and the TCAM enabling extremely fast lookups for large scale networks, because we have a lot of data that is coming in and going out, so we need something that operates at a higher level. So now that we have seen how packets are classified and forwarded based on their given address, and we said if there's two matches for the given address, we use the longest prefix matching technique. So we want to see how they are transferred on across the router. This is the role of the switching fabrics that works internally. So we have N input ports that takes the incoming data. It would switch it from the actual signal into bits. And we said about how we can find the addresses and forward them. We have and output ports that would output the data. So the high-speed switching fabric is going to be something that works in the middle, as we said, that connects the input to the output ports and is responsible of moving packets from one side to another as efficient as possible. So in this diagram, packets arrive from the left and they leave, they go through the switching fabric and they exit out on the right. So the design of component is going to be critical here that we have because it determines how fast the router can handle data traffic. So the concept here is going to be the switching rate, which defines how quickly can we move packets from one side to another, from the input to the output. So it's usually or typically measured as a multiple of line rate. So for example, with n input ports, we ideally want a switching rate of n times line rate. So that means the fabric should be fast enough to move packets simultaneously from all inputs to their outputs without any delay. So in high performance routers that we have, achieving this rate or ideal rate is going to be the optimal rate for us to ensure reliable delivery, smooth delivery, and congestion-free internal packet flow. Once the packets or once the data enters the input ports and goes to the switching fabrics, the switching fabrics have different, you can think of topologies or structure, and we need to speak about the different types of switching fabrics. And memory was the original or old-based switching fabrics, then it transferred into bus, and now we use interconnection network. So these are going to be the different types we have, and each comes with its own different performance and scalability trade-offs. So the first one that we have is memory-based. So packets are transferred to the router main memory, and the input port writes packet into memory, and the output ports later reads it. This is really common in early routers, but it is limited by memory bandwidth. And bus-based fabric, which is the second figure that we have here, meaning that all inputs and output ports share a common bus, meaning that each packet across through the shared bus to its output port. So which simplifies the design a little bit when we compare it to memory-based, but still restricts the idea of having to work simultaneous transfers. The interconnection network is what mostly is common today. This would allow multiple packets to be transferred at the same time by connecting inputs and output ports through a grid of paths, basically multiple paths. And this approach itself scales best for high performance and routers. So these are the architectures on how routers evolved from single memory-based systems to parallel interconnection networks designed for massive data. So if we have a lot of data that comes through, our memory is going to be overflown. That will delay a lot of things. Bus is using, it's not using all the other routes that we have, and the interconnection network is using everything at once. So obviously we would want to use the interconnection. So we want to focus on each switching architecture. So the first one we have is the first generation of routers via memory. And we said that in these routers that we have, we would have the CPU controlled switching process that treats the router much like traditional computers. So each incoming packet is going to be copied from the input port and is going to be stored into the system memory before sent to the output ports. So let's take a look at how it looks. So we have the data that is sent. After sent, we take a copy of it and we store it in the system memory before we send it to the output ports. So the CPU uses the forwarding information to decide where the packet should go next. Then they're copied out of memory to the correct output port, ready for transmission. However, this design requires two bus crossing per packet. One onto the memory and one which can become a performance bottleneck for here that we have. And then also something to note, as the link speed increased, the memory bandwidth could no longer keep up. So it limits the router overall throughput. And this is gonna be this, yeah,
You mentioned the second bus was one.
the second process.
You said there was two buses.
Yeah, within the switching via memory, there's gonna be two buses, one that copies, and the other one is gonna be delivering the information. Yeah. So that is the traditional base that was found in early networks. Switching via bus, that kind of replaced the memory-based architecture. So the packets move from the input port memory to the output port memory using a single shared communication bus. So each packet is going to be placed onto the bus, and the correct output port reads it from the bus as it passes by. And the limitation that we will have with this architecture is that the bus with the bus architecture here is that only one packet can use the bus at a time. So the overall switching speed depends on the bus bandwidth. So when you speak about the performance of routers, like high performance routers, usually uses a 32 gigabytes bus that is found in Cisco 5600. So which is sufficient for like small or access routers. But however, as traffic scales up, that shared bus that is being used become also a bottleneck. So it cannot support multi transfers at the same time. So this design is an improvement based on memory based, but it still has a limitation of scalability for high speed backbone routers. So switching via interconnection network. So after bus-based routers, the next step was to use interconnection networks. So that is kind of developed by multiprocessor systems, or the conceptual idea of that was developed by the multiprocessor systems. So these designs would connect multiple input and outputs using a grid or a network of smaller switching elements. So that allows multiple packets to move at the same time. So the first example here is the crossbar switch that we have, and that is going to be the top image we have. So each input can directly connect to an output and enabling parallel transfers, as long as no two packets compete for the same output ports. Larger routers often use multi-stage switches, where we have N by N switch. So that is built from several smaller interconnection stages. And that structure itself helps performance more without requiring one massive single switch. The interconnection networks or that architecture also exploit parallelism by breaking datagrams that we have into fixed length cells before entering the fabric. So these smaller cells independently through the network and are reassembled at the output ports. So this design really helped and dramatically increased the throughput and allows modern routers to handle many packets, many transfers, many data entering and exiting out in an efficient manner. So we will see here that when we have new data that comes or new packets, they could take several paths that would reach the output ports. Obviously, rather than having one single crossbar, multiple or the memory base. So this is the more efficient based system that we would have, or architecture is the switching via interconnection. This slide here just expands on the network by showing how routers scale performance using multiple switching planes in parallel. So each plane would act as its own independent switching fabrics that would allow packets to be processed at the same time across different paths. So the key idea here is parallelism. So we have multiple packets that can move through the router at once, dramatically increasing the throughput. Yeah.
Is this a mark there, like, how the $8 bus?
Yeah, exactly. So we have each plane has its own like switching fabric. So that makes it more efficient. So the idea of with the idea of parallelism. So to talk a little bit about a little bit about real based or a real world example, the Cisco CRS router. Have you guys heard of that? I have not heard of it well or not. I really determined like know about it unless I read the book before this lecture. It uses 8 separate switching planes, and this is basically the idea or methodology that we discussed with switching the interconnection. And then each of these planes is built to a 3-stage interconnection networks that allows efficient non-blocking data transfers. So with this design, we know that is the most efficient base, and the routers themselves can reach hundreds of terabytes per seconds when it comes to the switching capacity. So this architecture is the mostly one that is used today. The modern, it's the most modern high-end router design, where parallel switching ensures both scalability and fault tolerance. So that is where we are so far in the network layer. So we moved on from the transport layer to the network layer, and we discussed about the routing, what is in the router. We talked about the route, the data plane, control plane. We talked about what is the responsibility of the network layer as a big view. We talked about the traditional based routing versus the software defined based. We talked about a little bit about also what is inside the router, which is the input ports, the switching fabric, and output ports. And we talked about how these switching fabrics have different architectures that have been developed over time. And the interconnection is the one that is mostly used wide today. So that is it for this lecture. I will see you next week on next Monday. So if you have any questions, you guys are dismissed. Thank you.
Yeah.
Uh-huh.
First. It's gonna be online as well, or it's gonna be present?
No, for the final is gonna be similar to the midterm. It's gonna be online. The date is gonna be, it's really gonna depend on where we fall off with the modules and how well we wrap up the modules. So it might be, I might assign it before Thanksgiving so that you can leave for Thanksgiving and then you don't have anything after. Or it could be where it should after Thanksgiving.
That's towards the next, because I'm trying to plan it ahead.
Okay, so when it comes to planning, it's gonna be online, so you can plan that. You don't have to come in person, that is for sure. In terms of the time, it's gonna be known as we approach. Either it's gonna be on that final week or before Thanksgiving. So I don't wanna assign anything on Thanksgiving.
So yeah, Thanksgiving's like the 20th or something, the day before, are we gonna have class that day, or
Thanksgiving falls on a Wednesday, right?
Thanksgiving's on Thursday?
Thursday?
I think it's the 28th. It's Thursday the 27th.
I think we will